Hi there, it's Chem Coach Powers, and we are about to learn a little bit more chemistry in our physical science class. Today, we're going to talk about compounds and molecules, specifically talk about the structure of those compounds and molecules, different ways to represent those structures, how those structures can affect the properties of those compounds or molecules. So let's get on to our journey today and talk about what we are going to learn. This is chapter 6, the structure of matter, and specifically 6.1, compounds and molecules. Explain what it is that holds atoms together, chemical bonds, right? We'll learn a little bit more about those. Describe 3 ways to show the structure of compounds. So we'll talk about structural formulas, shape-filling models, things like that. Explain how the structure of compounds can affect their properties, right? These are our objectives today as we dive into this. But before we start, we need to review, because we've talked a little bit about compounds and molecules before, but it's important that you can distinguish the difference between a compound, a molecule, a mixture, things like that, right? So are these elements or compounds? Are they atoms or molecule? F2, that's an element, but it's also a molecule. It is not a compound. Remember, compounds have 2 or more different types of elements that they have involved in them. This is just one type of element, and so that's just a molecule, right? But it's also an element. This is an element, not a compound or molecule. Remember, big letter and small letter means that we've got an element, and it's just a single element. If there were 2 capital letters, then maybe we'd have something different. Here we have 2 capital letters, a capital H and a capital I, which must mean we have a compound, okay? Now, the actual definition of molecule may, apply to this one, but sometimes it doesn't apply to certain compounds, okay? So this is a compound, it's also a molecule. All right, now, the number of atoms of each. Remember that you need to know how these things are grouped together. So I've got 2 hydrogens, 1 sulfur, 1 calcium, 2 oxygens, and 2 hydrogens here, right? Total number of atoms here is going to be 5. Total number of atoms here is going to be 3. What's the difference between a compound and a mixture, right? Well, the compound has properties that are unique when it becomes the new thing than what they were before. The mixture has its individual components retain its own properties. And that's a real big difference. What we're going to talk about today is compounds. HI would have a new property that H and I would not have had. H has its own properties, I has its own properties, and if you mix them, they both still have their own properties. But if I combine them in a compound with a chemical bond, this thing will now have some new properties. That's a big idea, right? All right. So let's continue going on. Let's talk about why this is important. Why would this matter to you as a student? What's a compound? Who cares, right? Well, think about this. Why is wet clay bendable? Dry clay becomes crumbly, and clay that's fired in the kiln becomes hard, and it's not easy to break or bend, right? So let's talk about it. Well, water that's in wet clay is going to act like ball bearings, and those little clay molecules, those little sand, kind of like sand pieces, right? They're going to be moving around each other because the water is basically lubricating that, and it allows for the clay to move around. When it dries out, that water, which was a molecule that was in there before, has now evaporated out, and so now that water is no longer acting as a ball bearing, and so now those clay particles have extra friction. They're not going to be able to move along each other very easily. They stick on each other, right? They're still not attached, though. They haven't bonded to each other yet, and so they are not going to be considered a new compound. They're just still a mixture, and they're just still hanging out next to each other. However, if we fire that clay in a kiln, we can get bonds to form. We have new compounds that are being formed, and that makes the object hard, and it's no longer able to dissolve in water, and so it's going to be able to stay together in a new hard solidified form because we formed a new compound. Okay, so this is how your everyday life might apply to the stuff that we're talking about now. A chemical bond is defined as the attractive force that holds atoms or ions together in compounds. Now, we are going to have a type of bond in an ionic compound, and we're going to have a type of bond in a molecular compound. Okay, but the bond is going to be the attractive force between them every time. Why does a bond form? Well, let's think about that. A bond is going to form in order to reach a lower potential energy state. Okay, so the big thing here we want to think about, bonds are typically going to form so that the individual atoms will be able to get to a lower potential energy state as a new combination than they had before. And they're usually trying to share electrons or transfer electrons, right? Sharing of electrons is covalent bonding. Transferring electrons is the ionic bonding. The substance is going to blank energy when bonds are formed. So when I form a new bond, I've gotten to a lower potential energy state. Therefore, I went down in my potential energy. I must have released some energy. Okay? If I'm breaking the bonds, it's going to take energy to break bonds, all right? And so this is going to basically give the absorb, there it is. It's going to absorb energy to break bonds. Now, this isn't the case all the time. There are definitely plenty of examples where you would end up having energy absorbed when you form bonds and broken when you, released when you break bonds. But in the majority of the cases, this is the way that things are going to work, because that's the reason that they are going to form bonds, so that they can reach that lower potential energy state. Now, when we think about something like fire, fire is a chemical reaction where you have something breaking bonds and something forming bonds. And so fire is this really hot reaction. We know the energy is released in that reaction, but where is the energy coming from? The initial reaction doesn't start until you apply that accelerant to it, right? So if we get that match to start it, then we can get that whole thing working if it's like a fire, that's burning wood or something. And remember that it's got to break those bonds of the pieces of wood that are there, and then it forms new bonds, and it forms carbon dioxide. Now, carbon dioxide has a lower potential energy state than the wood did, than the initial, carbohydrates and the initial, cellulose fibers that are there. And so what happens is I put energy in, and it breaks some of that cellulose bonds up. And so it took energy to break those up. But now once they form new bonds with carbon and oxygen, now that those have been released, now they're at a lower potential energy state. So they release this extra energy. So this extra energy that you get from fire is all about the energy that comes from some of those bonds that were storing energy. Those little bonds stored energy, and they took energy, breaks them, and so they let out. They were now free, and now as they form new compounds, they get to a more stable state, and they release this extra energy as they get to that more stable state, and that's where that extra energy comes from in the fire. Pretty cool, right? All explained according to chemistry. All right, so let's talk about structure of chemicals, right? The chemical structure. How can the structure of chemical compounds be shown? We have basically three different ways that we want to show these, okay? Structure of chemical compounds can be shown with these three different models, about to get to there. But first, let's talk about what we mean when we use that term chemical structure. We're just talking about the arrangement of the atoms, okay? Now, we can show this arrangement in different ways. There's different techniques, and I'm going to show you three of those different techniques. But the structure is the arrangement of the atoms. So sometimes we're going to represent bond lengths and angles. We're going to have a particular type of structure that does that. And what do I mean by bond length? Well, that's the average distance between the nuclei of two bonded atoms. So sometimes in a particular model that I have, I might have a particular length of a bond. If you notice, these have a particular length to them, okay? And I have another molecule over here that has shorter green bonds, and that's representing a different bond length, okay? So bond length is the average distance between the nuclei of two bonded atoms, and the bond angle is the angle formed by two bonds of the same, or to the same atom. So here you can see that I have an angle that's actually about 109.5, no, this one's actually 120 degrees, okay? That's a 120 degree angle. But here on this compound, I have 90 degree angles everywhere. Okay, so that's different. This is different bond angles. Over here, I have these ones are 109.5 degree angles. Okay, so we have all sorts of different bond angles that are represented, and it's going to give you different shapes. And the reason that those bond angles form, you'll learn more about in chemistry, and you'll learn why they're different from each other. So we have a type of structure called the ball and stick model. Okay, ball and stick models, basically the atoms are the balls, and then the bonds that hold them together are the sticks. So here we have a ball and stick model. Okay, balls and sticks. Okay, ball, sticks, ball, sticks. All right, that's a ball and stick model. And now you notice that this is great for showing bond angle. Oh, 104.45 degrees here. And then the bond length, if I choose a certain size of stick, then I'm going to get that certain length involved there, right? And then I also have structural formulas. Here I just put chemical symbols, and I can use little angles, but I'm not actually going to be really making sure that those angles are correct, okay? In ball and stick model, I'm trying to make sure those angles are correct. In a structural formula, I just want to show the letters that are there and the general location that those letters are with regard to each other, okay? And then I can have a space filling model, and this is showing the actual space filled by the atoms. So my hydrogen is filling up all that space, and it's combining with my oxygen, and my oxygen and hydrogen are sharing a certain space inside there. So we've got ball and stick, structural, and space filling model. Those are three models that I want you to become familiar with, okay? Three different ways to show the structure of chemicals. But remember, the bonds can bend, stretch, and rotate. And they're not like these sticks like we try to, show you in these little things. They're not actually like these sticks that'll actually not really bend. They actually do bend. And it's actually probably better to represent the bonds as springs, flexible springs, because those bonds can move, and they do move. And so when we give you bond lengths, we're typically giving you an average distance instead of, a defined, definitive, always the same distance, right? Bonds are going to hold the atoms together tightly, okay? So when I have a mixture, then I don't have them attached to each other. Or like when we're talking about the clay, right? When it was wet, they were moving around each other. And even when it started to dry, they still were not attached to each other. They could still break apart really easily. The bonding that takes place when the atoms are grabbing onto each other with a bond, that's holding them together tightly, okay? So here's an example of the stick versus the spring. This is actually a little bit more realistic, where the distance can actually change between those two atoms, okay? All right, so how does that structure affect the properties? What determines the properties of a compound, okay? Well, it's about the shape. It's about the shape, okay? The structure determines the shape. This is, what I'm representing here is actually graphite. Now you'll notice that these are white these white sticks here, those are called hydrogen bonds, and they're not really strong bonds. We're just showing that, these are actually kind of flexible. You can kind of move them around. But these are hydrogen bonds, and this is graphite. This is the stuff that you have in your pencil, right? Pencil lead. And it's basically a sheet, and if I pulled this piece of graphite off, I could pull them off, from the white things. And basically, when you write with a pencil, you are letting one sheet after another sheet after another sheet of the graphite just slide off, breaking those hydrogen bonds that keep them loosely attached here, and then allowing pieces and pieces and pieces of this graphite to just lay on the paper, okay? This is a stronger bond. Now this, again, those white bonds or hydrogen bonds are not truly actually bonds. They're just attractions. Now these are bonds. These are still considered bonds. This is a basically salt, sodium chloride, okay? This is like a salt molecule. Notice how there is an interconnected, like every single, if you look at one thing in here, you can see that it's attached by bonds to 1, 2, 3, 4, 5, 6 different things. And if you paid attention to what this one is surrounded by, you could talk about like in the actual salt crystal, you've got 6 different things that surround it. And so each of these is interconnected. And because each one is connected to the other because of positive and negative attractions, this is actually a really strong structure compared to that graphite. Okay, so this chemical bonding has determined its properties. This is an ionic crystal, and it's a strong crystal. Strong crystal for an ionic crystal. Let me show you some water. Okay, I've got water right over here. And get this off. Now, this particular water isn't the liquid form because that wouldn't be a good example to compare to a salt crystal. This is an ice crystal. And again, now you're going to notice these white ones again. The white ones are the hydrogen bonds. And notice that this is actually forming hexagons. Okay, why do snowflakes always end up as hexagons? because they naturally form these bonds in the shape of these little hexagons. But these hydrogen bonds are not nearly as strong as the green bonds. The green bonds are the covalent bonds. Those are stronger than the white hydrogen bonds. Lots of covalent, or lots of, these are actually called ionic bonds. These are lots of really strong bonds together in bunch of interconnected ways. These are not interconnected in quite as many places. Look, I've just got one water molecule, 1, 2, there's only 3 water molecules attached to that one water molecule, right? At least in this case. And if we had some more, we could have some more, but it would be 3 others, and there'd be another one here, right? And another one there. So there's still always just gonna be 3 water molecules attached to one water molecule. It's not gonna get as strong, and they're not the covalent bonds, they're the hydrogen bonds. Now, this is the strongest crystal that is known to man. This is the basically an imitation of that crystal. And what is that crystal? Strongest one known to man in nature, right? And that's the diamond. Now, this is made up of a bunch of covalent bonds, but again, they're all interconnected in a very strong way. And this one really, it's 1, 2, 3, 4 are connected to each one. So it's very similar to the water, okay, in terms of how many connections there are. But these are all covalent bonds. These are not. This is called a covalent network crystal. It's the strongest crystal we have. This is just hydrogen bonding that puts that together, okay? This is ionic bonding that puts this together. This is stronger than this. What properties does that have? Well, I cannot cut this apart as easily as I can cut this apart. This is going to have a higher melting point than this will, right? So these both will have higher melting points than the other ones we were just talking about. And so the structure of the chemicals, how they are interconnected, determines their properties. And so that's kind of cool to realize that every chemical is connected in different ways, and their different structures determine their different properties. So compounds with network structures, like the salt, okay, sodium chloride, or like the diamond, those are going to have strong bonds, and so they're going to be solids typically, right? Quartz, silicon dioxide, diamond, like I talked about. Silicon dioxide is basically quartz, right? It's the stuff that you would, make glass out of. You've seen plenty of quartz rocks in the mountains, I'm sure. Atoms are bonded in a strong, rigid structure. It would look very much like the diamond or the salt crystal, depending upon its actual number of attachments. Now, some networks are made of bonded ions, and so those strong attractions between those oppositely charged ions give ionic compounds higher melting points and boiling points. And so that's why this is salt, this has the higher melting point and boiling point because they're ionic compounds that are keeping them together, or ionic bonds keeping them together. Here we just have hydrogen bonding keeping these together, not nearly as strong, lower melting point. So that's our table salt. I already showed you that one. Tightly packed, sodium ions are positive, chlorine ions are negative, and they're in an interspaced arrangement there, where 6 of them are attached to every one. All right, so let's continue talking. Some compounds are made of molecules. So we have the ionic compound, and then we have the molecule. We talked about water. These molecules are oftentimes going to be liquids or gases, okay? Some of them are going to be solids as well, obviously, but we also have liquids and gases. When the liquids and gases, by nature, tells you that their bonding isn't as strong because they've been breaking, the bond broke earlier with regard to the amount of temperature required, and so now they're moving around each other. Okay, so you're going to have varying strength. Again, the diamond, covalent bond, the strongest one we have, but that was because of the interconnection. The water doesn't have that same interconnection. These attractions between water molecules are called hydrogen bonds. We already talked about that. I showed you those little white ones that we had. The hydrogen bonds are not as strong, and again, we usually talk about them more as an attraction, an intermolecular force, than we do an actual bond. It's just kind of the way we talk about it. All right, and you guys already saw some water. It's just another example of water molecules interspersed and attracted to each other. The hydrogens of one always attracted to the oxygens of the other, and so they form these little hexagons. Okay, so let's see what we've learned today. Can you explain what holds atoms together? Yeah, bonds. Chemistry is about the chemical bonds, right? So the atoms are held together by the attraction. And again, remember that attraction is an attraction between the nucleus of one atom and the valence electrons of the other atom. That's what brings them together. 3 ways to show the structure of compounds. We have the ball and stick model, we have the structural formula, and we have the space filling model. Okay, it's our shape model. Explain how the structures of compounds can affect their properties. Well, Their interconnectedness can make a big difference on their boiling point. The types of attraction, ionic bonds are stronger than covalent bonds because there's a bigger attraction between those different things that have different electronegativities. Hydrogen bonding is not as strong as covalent bonding, which is not as strong as the ionic bonding, unless you're in the case of a network covalent solid like diamond, right? Okay, so I think that's covered it. That's everything we wanted to talk about today. I hope you've learned a little bit more about bonding, and I hope your light is brighter because we have shined some light in your mind and in your life. So go shine that light in somebody else's life and be kind to each other. God bless you and have an awesome day.